Let's say you're a doctor, and you have a patient sitting in your office, and he is complaining of heart trouble. A standard thing to do for such a person would be to order an electrocardiogram in order to record the electrical activity of his heart. The result of such a test is called an EKG tracing. And what that is basically a plot of the voltage of the heart over a given time period. In this video, I'd like to go over what a typical EKG tracing would look like. Let's think about how the heart behaves electrically while it's trying to beat. So between beats, when the heart is at rest, all the cells inside of the heart are negative with respect to everything surrounding them. So the whole heart is this massive negative charge. But then, if we overlay the conduction system of the heart, we'll see what happens when the heart starts to get excited and starts to beat. What happens first is that a cell in a structure called the sinoatrial node, or SA node, gets excited and becomes positive. And that positivity spreads throughout the heart via a system of fibers called Purkinje fibers until the entire heart becomes washed in this wave of positivity. The effect of this is that it looks like a wave of positive charge is traveling from the sinoatrial node to the rest of the heart, like so. Now, if we were to place electrodes on either side of the heart like this, what would we detect? Well, if we were to put voltage on our y-axis and time on our x-axis, we would see that when the heart started out completely negative, at its resting state, there would actually be no change in voltage. This state is said to be baseline, and this is because there is no electrical activity. But then when the cell in the sinoatrial node decides to wake up and say, hey, I'm going to turn positive, then what happens when the wave of positive charge overcomes the heart is that it looks like positive charges are moving from the negative electrode to the positive electrode. And then you would expect to see an upward deflection on the voltage tracing like this. And this is because the positive electrode detected a positive wavefront moving towards it. We know now that all of the cells in the heart are positive on the inside, they're excited, and so the entire heart is in a positive state. But eventually the heart has to reset, and all of the cells have to go back to being negative on the inside, and this is because the cells need to relax in order to prepare for the next cycle, in which the heart has to pump again. And so for this to happen, a wave of negative charges travels from one side of the heart to the other. So let's say we have our electrodes placed on either side of the heart again, like this. What would we expect from the voltage tracing that comes from these electrodes? So from that, you might expect that your voltage tracing will look something like this, with a negative deflection. But actually, we don't see a negative deflection. We see a positive one. Now, why could this be? Well, let's think about how you could get a positive deflection. Well, you could get it when a wave of positive charges moves from the negative electrode to the positive electrode, but you could also get it when a group of negative charges moves back from the positive electrode to the negative electrode. And it turns out that that's exactly what happens in the heart. When repolarization occurs, that is, when all the heart cells are resetting, the wave of negative charges that results travels from the positive electrode back to the negative electrode, back the way it came. And this would explain our positive deflection. So if you guys understand that logic, then pat yourselves on the back, because that means that you're well on your way to understanding what an EKG tracing from a real patient would look like. Now, before I go ahead and show you what an EKG tracing from a patient would look like, I'd like to introduce one more concept to you, and it's a term called a cardiac cycle. And all a cardiac cycle is the time it takes for the heart to pump once. In order for the heart to pump, the cells in the heart have to get excited. That is, it has to experience a wave of depolarization, or positive charge, which is what we saw on the previous slide. And the cells have to reset again and go back to the negative state. So the heart has to also experience one wave of negative charge, or repolarization. So a cardiac cycle electrically consists of the wave of positive charge that goes from the SA node all the way out to the rest of the heart, and it also includes the wave of negative charge occurs when the entire heart is resetting and going back to the negative state. And the reason the cardiac cycle is called a cycle is because it repeats, as the heart has to pump over and over again. And this is important to EKGs because we should also see a cycle of electrical activity on our voltage tracing. Okay, so here's the moment you've been waiting for. What does a voltage tracing coming from an EKG actually look like when it comes from a patient? And what you see on the screen right now is what the voltage tracing would look like. Again, on the y-axis you have voltage, and on the x-axis you have time. And what I've drawn for you here represents one cardiac cycle, that is one beat of the heart. So I'm going to break down this diagram for you so that it doesn't look so intimidating. And it turns out that each deflection that you see on the diagram actually has a name for itself. So going from left to right, the first hump on this diagram is going to be labeled with a P because it's called a P wave. And then as you continue along, you see that there is a negative deflection, like so, and that deflection is called a Q wave. And then the voltage tracing skyrockets and goes into a positive deflection, which is called the R wave. Then it dips back down and goes below baseline in a negative deflection again, and that is called the S wave. And then finally, after a bit of time back at baseline, the voltage tracing ends in a hump, and that hump is called the T wave. So you can see that medical people are pretty fond of using letters of the alphabet, but these letters are important to remember because they're going to be used over and over again in any study of EKGs that you might undergo. Now, something else that I should tell you is that the Q, the R, and the S, since they come together, are often called collectively as the Qrs complex. But really, each component of this complex has its own name, Q, R, or S. So this might sound kind of scary at first, but it'll mean a lot more if we kind of break down where each of these deflections from the baseline actually come from. So to see how that works, let's think back to an image of the heart and remember that the top two chambers of the heart are called the atria, and the bottom two chambers are called the ventricles. And so we want to know how we get this bizarre looking voltage tracing from the electrical activity of our heart as it's trying to pump. So where does the P wave come from? Well, that actually comes from the atria depolarizing or getting positive. So as the wave of positive charge takes over the atria, the electrodes that are sitting on the patient's skin detect that wave of positivity and read out a positive deflection. All right, now where does the QRS complex come from? Well, that turns out to come from ventricular depolarization. And for now, don't worry about why you get a Q wave that is deep and an S wave that is negative and you get an R wave that is positive. Just consider the Q, the R, and the S to come together as the package and focus more on the R wave, which is way, way positive, because really there's a wave of positive charges moving through the ventricles. Now let's see where our T wave comes from. So that actually comes from the heart repolarizing. That's when the negative charge returns to the cells and there's a wave of negativity that spreads throughout the heart. But the repolarization that is shown in the T wave isn't actually for the entire heart, it's just for the ventricles. And so you might be wondering, okay, well, what happened to the atrial repolarization when the atria decided to become back to the negative state? And actually, atrial repolarization occurs somewhere at the same time as during the QRS complex. So it's actually buried somewhere in this part of the diagram. But because the QRS complex is so strong and the deflection is so high, especially for the R wave, we don't actually see atrial repolarization. Now there's another important thing to notice from this diagram, and that is the QRS complex especially the R wave, is generally a lot narrower than the T wave, which is this wide hump. And the reason that is so is because when the ventricles depolarize or become positive, they do that because positive charges are moving through a system of fibers called the Purkinje fibers. And that is basically a highway for charges to move really, really fast throughout the heart. But the T wave comes from ventricular repolarization, and it turns out that when the wave of negative charges is traveling throughout the ventricles to reset them, they don't take the Purkinje highway. Instead, repolarization occurs on a cell-to-cell basis, and so the wave of negative charge is actually moving a lot slower than the wave of positive charges did. Okay, so we understand that. But now I have to tell you that the diagram that I've shown you right here is actually not the full story. It's actually only one out of several ways that an EKG tracing could look. So the reason I've drawn it this way is because this is really the stereotypical image you're going to see when you look up EKG tracing on the internet or in a book somewhere. And since there are so many variations in how a tracing can look, it's very, very important to go over and really understand the terminology that we use to describe a tracing. So I'm going to give you the same diagram again, and what I'm going to do is sort of reiterate some concepts that we went over before, but there will be some additions that will be key to understanding how variations in the tracings work. So again, we have our P, Q, R, S, and T waves, which I'm going to label. And now what I'm going to do is sort of walk you through what the definitions of each wave actually are. So the P wave is a small rounded hump, and it should appear on all normal EKG tracings. So if it's absent, that means that there's something wrong. And the reason is because if the heart needs to pump, then there has to be atrial depolarization or positive charge moving in the atria. If there isn't that wave of positive charge, it means that the SA node isn't working. And the SA node is the thing that wakes up the entire heart and tells it to be positive. All right, so the Q wave, definitionally, is the first negative wave of the QRS complex, or the first negative wave that comes after the P wave. And this wave doesn't actually have to be present in all normal tracings, and it often isn't. Okay, the R wave is the first positive wave of the QRS complex, or the first positive wave that comes after the P wave. All right, the S wave is the second negative wave of the QRS complex, or it is the negative wave that comes after the R wave. And finally, the T wave is always the hump that comes after the QRS complexes, but before the P wave. Now, you might think it's silly for me to be going and spelling out what each wave is to you, but I'm going to walk you through some examples in a moment that kind of shows you the intricacies of all of this terminology. And when you go back and look at these definitions after walking through these examples, the reason I put them there might be a bit more obvious. So let's start off with what we already know, our typical EKG tracing, which is completely labeled. So let's go ahead and take one component away. So how would we label this particular tracing? Well, the first thing that we see on the tracing is a rounded hump that's kind of small, and that's our P wave. And then after that, we see a negative deflection, and the first negative deflection that comes after the P wave is our Q wave. And then we see a positive deflection that's very big, and that's going to be our obvious R wave. And then after that, we would have had an S wave if the tracing was completely textbook style, but it's not there. And so then after that, we have our big rounded hump, and that hump is the T wave. So that seems simple enough. Now let's go to a different example, where now we've taken away a different part of our tracing. So again, we start out with our P wave, and then the next thing that we hit is a positive deflection. And the first positive deflection is going to be the R wave. And then the negative deflection that comes after the R wave, what would we call that? So you might be tempted to say that's a Q wave because it's the first negative deflection of the QRS complex, but really it came after the positive deflection of the R wave. And if the negative deflection comes after the R wave, it has to be an S. And then finally, we have our T wave. Now let's say we have this kind of a tracing. So we have our P wave, we have our T wave, and then we've got our sort of abbreviated QRS complex in the middle, except that it's not really QRS, there's only one part of it. And that part we're going to call R again because it is the positive part. So the positive part of the QRS complex is always going to be the R wave. All right, finally, let's go to this tracing where we have our P wave and our T wave, and we have something in the middle that we could call our QRS complex, but it's pointing downwards rather than upwards. And so, since it is the first negative deflection that comes after the P wave, we're going to call it a Q wave. So this tracing does not have an R, and it does not have an S. And I'd like to emphasize that the terminology is kind of tricky sometimes, but with some practice it'll become a lot easier. And an important thing to note is that I've drawn all of these tracings just for the sake of exercise, but that doesn't mean that all of these tracings are normal. In fact, if you have just a Q wave, for example, in this tracing right here, that's actually a really bad sign. It signals some kind of pathology or some kind of problem is happening inside of the heart. But all of these patterns are possible. It's just that they're not all necessarily normal.